Now, in the last couple videos, we spent some time talking about example number 1, and this was a process again that was kind of broken up into several different parts. And this process is what we call hypothesis testing. Now, again, we're going to be introducing several new pieces of terminology to help kind of summarize this many parted problem into kind of a one single uniform process. And the first thing that we're going to do is we're going to focus on those hypotheses and try to give them some more distinguishable names rather than just hypothesis 1 and hypothesis 2. So we're going to see that we always have two different hypotheses that we're going to be working with. One of the hypotheses asserts that the sample statistic just happened by random chance. Up above, you might recall that that was actually just hypothesis 1. It said our sample was lucky. We just got it by chance. And that's the one that we test. What we're going to do, though, is we're going to rebrand that hypothesis. We're going to refer to that as the null hypothesis. And we're actually going to give it the value, or not the value, but the shortcut symbol of h with a little 0 on it. Okay? And this is always going to be a hypothesis that claims that our parameter of interest is equal to something. Just like, again, if I go back up above, I had p equal to 0.50 in this hypothesis. So this hypothesis that claims that we're going to just have gotten our sample just by luck will always have some value equaling something else. Now, the other hypothesis up there is what we're going to refer to as the alternative hypothesis. We're going to change that to be a label of H1. Instead of calling it hypothesis 2, we're going to have H1. Now, this is always going to be the hypothesis that's going to have one of these symbols in it. It'll either have a less than, greater than, maybe a not equal to sign, and its job is to always assert how the population parameter might be different than what it was claimed to be up above in the null hypothesis. So we're going to go ahead and try to use this language down here in example number 2. I'm going to go ahead and work quickly here with through parts A through C, and then I'm going to leave parts D through G for you to go ahead and try on your own. Let's see what we have here. A scientist claims to test if a new treatment has a better cure rate, or a scientist, I guess this is kind of awkwardly worded. Let's suppose that a scientist wants to test to see if a new treatment has a better cure rate than a traditional treatment, which cures only 60% of patients. So maybe, this is like some, new vaccine or something for some big virus. And, maybe there's something like, hey, what we currently have will cure about 60% of people, and this person thinks they have something better. So is it actually better? How do you know? Well, in order to test whether the new treatment is more effective or not, well, you got to do some trials, got to do some clinical trials. So maybe they take a group of 50 patients and they give them the new treatment. Assume that each person's results are independent of the others, and we're going to say that 34 out of the 50 of the patients in the test group get cured. Okay, well, is that enough reason to believe that the new treatment has a better cure rate than the traditional one? Okay, so notice we're going to have the same set of questions that we did back in example 1, just about a new scenario. So there is a population parameter that the scientist is interested in, and that population parameter would be the percentage of all people who will be cured using the new treatment, right? I mean, the scientist is definitely wanting to know this value. This is, again, our moment where we can say, this is P equals, and I don't know what it actually is, right? The scientist doesn't know what percentage of everybody is going to get cured with this new treatment. They're hoping it's better than the 60% mark, but we don't really know for sure. Now, what is the sample statistic that the scientist, cross that out, has? Well, what the scientist does know is the percentage of the 50 tested people that were cured by the new treatment. That number the scientist actually has. And in fact, we can calculate it. So this would be a value of p hat, and we have that value, let me write it here in a slightly different color, but we have that value as 34 people out of 50, which, if you crunch it out, is actually 68%. So again, we have to admit to ourselves that we don't really know what P is going to be still, right? Because I mean, there's millions, billions of people in the world. So how do I know what percentage of all of them would get cured? I don't know that. It could be 68% on the nose. It could be higher. It could be lower. I'm not quite sure. But I can start to go ahead and state some hypotheses. I'm going to state my null, which is H0, first. So notice instead of writing H or hypothesis 1 and then putting down my colon, I'm now just going to say H0, my null hypothesis. What would it say? Well, it would say, remember, it's a boring hypothesis. So it's going to claim that the cure rate for the new treatment, is just as good as the old treatment. Right? Like the scientist hasn't come up with anything too miraculous here. It's essentially just an unsuccessful project, right? If I was to put that in symbols, down here we're kind of saying that if the new treatment is just as good as the old one, then what percentage of people should it cure? Well, based on what the problem said, the old treatment only cured 60% of patients. And so if they kind of do the same amount of curing, then here we're going to claim this is 60%. Notice here, my H0 always has an equal sign in the symbolic representation. When I write down my H1, this is going to be the more interesting one that says, well, you know, it's possible, right, that obviously the new treatment could be just as good as the old, and maybe our sample was just a bit lucky, but it could also be the case that the new treatment is better than the old treatment. And that's maybe why in this sample we're seeing over 60% of people get cured. So in here we could say, oh, okay, so that would mean that the cure rate would be over 60%. Now, which one of these is right? We don't know. We have to make an educated guess. And I'm going to ask you to work through parts D through G on your own. You can check the solutions up in Blackboard. But this is going to be very, very similar to exactly what we did in number 1. You're going to try on this null hypothesis, and you're going to see how it fits to say that 60% is the right value for P, and we just got lucky by getting 68%. Well, I need to see if that fits or if it doesn't fit. If it fits, we'll kind of keep this hypothesis. And if it doesn't fit, we'll ditch it and we'll go with H1, this other hypothesis. But remember, at the end of the day, you're just making your best educated guess. That's all this process is. It's an educated guess based on some good numbers. And keep that in mind as you answer part G.